Now that you've learned direct and inverse variation, we're going to go ahead and take the idea of inverse variation a little bit farther. So if you remember, inverse variation was y equals k over x. Now, we use the form y equals k over x because most of the time we use y to represent a function. And so if we rewrite that, you can see we have the function notation f of x equals a over x. And so we basically replace k with the value a. Now, that creates a function. And if you keep in mind, if you remember, the a value in all of our other functions always kind of represented a multiple that either stretched or compressed the given function. And so we'll see how that looks in a little bit. Now, the main parent function that these all stem from is what we call the reciprocal function. And so we have 1 over x. And so 1 being the smallest value for a over x. And so you can look down here in the key concept box and get a general idea of what that graph would look like. Now, if you notice, as the graph, the red curve, gets closer and closer to the x-axis, it starts to kind of tend to get closer and closer but never cross or intersect. That is called an asymptote, and we reviewed asymptotes in the first semester. And so if you remember, the asymptote kind of acts like a barrier. Now, sometimes the graph will cross the asymptote. So basically what the asymptote is doing is it's dictating in behavior on the x-axis, and it's actually creating a barrier on the y-axis. And so we'll talk about that in more detail as we go into the next lesson. Now, if you also look at the key concept box, you can see the a, the h, and the k, and we can still do the same transformations to this function that we've been able to do to every other function so far. So this is just a quick little introduction to reciprocal function and how it stems from, or the inverse variation. In the next video, we will go over some sample problems. Now we'll take a look at an example of a reciprocal function as far as graphing it is concerned. If we look at this, it says graph f of x equals 8 over x. Now, very simply, you could do a t-chart for these, and you can see how in step 1 the t-chart is created a set of x and y values, and then in step 2 how we plot those values and create this kind of smooth curve. Now, generally speaking, you should just really kind of practice sketching these and understanding what the various a, h, and k values do to the reciprocal function. I'm not going to put a lot of emphasis on the detailed points and the exact graphs. Again, a lot of this will be sketching to understand the generic nature of these curves, and then also just being able to identify them or match them on Math Excel or on a test. So you can see very simply how this plays out. Now it says identify the x and y intercepts and the asymptotes of the graph, and it wants us to state the domain and range. Well, since the x and the y-axis technically are the asymptotes, it actually has no intercepts there, so it never touches either one of them. In this case, the domain is a set of all real numbers except x can equal to 0, and that kind of takes us back to what you saw in our function operations earlier in an earlier unit. So, and again, the range is similar, all real numbers except 0. So if you look at this next problem, go ahead and do this next problem. You can do a t-chart for both of them and try to do a smooth curve. I'm going to just go ahead and do this on the calculator so that you can at least get a visual of what they should look like in comparison to each other. Alright, so if we take a look at this, we have in the blue f of x equals 2 over x, and you can see how much closer that kind of hugs the x and the y-axis all the way down to the origin, and how the 12 is a much bigger number, so the a value is much bigger, so it kind of creates a kind of a curve that's a little bit farther away from the origin, if you will, and so that would continue to get farther and farther away. So if you did 50 over x or 100 over x, you could see the effect of what that does. So this just gives us a good look at what this graph does. Now, here's something that's very important. The two parts, so if we're just talking about 2 over x, if we look at the two blue parts, those are not two separate graphs there. those are the graph of the same function. So they're together. They're not two separate parts. Well, you see here in the notes, we call those two separate parts branches of the reciprocal function. Okay, and so you got to understand that they go together. You can't have just one or the other. They actually go together. Now, you can stretch and compress or translate these branches similar to the way we could do other functions. So if you look here, we have the a, the h, and the k involved in the reciprocal function and how it affects each of those different branches of the reciprocal function. Now we'll take a look at the last two sample problems in this lesson. Now, generally speaking, I'm probably not going to spend a lot of time getting detailed points on this using a T-chart. If that makes you feel more comfortable, that's fine. What I really want to focus on more than anything is how do we identify what the asymptotes are, and then just drawing a basic curve to meet those asymptotes. And so we'll just go ahead and take a look at this really quickly. First of all, the a value is a 1, so this is just the standard reciprocal function. The curve is not getting farther away from the origin, or in this case where the asymptotes cross. It's your standard reciprocal function curve. Now, we have x plus 1, and remember that h is always opposite, so this is going to go back 1. Well, that is going to tell us what our asymptote is. So basically what we're looking at here is we're looking at an asymptote of x minus 1. So we have x equals negative 1 as one asymptote, and then we have y equals to negative 2. The k is a negative 2, so the y equals to negative 2 is going to be our other asymptote. Okay, so if we plugged in a basic 0 for x, you could see 0 plus 1 is 1, 1 over 1 is 1, 1 minus 2. So we're roughly going to get this value right in here. And of course, we're going to try to keep this as close to the asymptote as possible without actually touching the asymptote. And we have a similar situation here. And again, this is just a quick and easy sketch. I'm really not trying to be too detailed. Let's take a look at the other parts of this question. It says identify the domain and range. Well, the domain is going to be all real numbers except any value that makes the denominator equal to 0. And so you could see a negative 1 would make this equal to 0. So x cannot equal to negative 1. Okay, and so we could write that in that way, or we could write that in interval notation, and you could see it written like this. So if you remember interval notation, we could say all values to negative 1, but not equal to negative 1, and then negative 1 and all values to positive infinity. And you could see it written like that. And then the range would not be together altogether too different. We're going to have all real numbers, except this time y cannot equal to negative 2. And so you can see the asymptote really dictates to us the values that are excluded from the domain and the range. And again, if I wanted to write that in interval notation, you would see it like that. And of course, the horizontal and vertical asymptotes, we've got that already. So let's take a look at sample problem number 3. This one's quite different. It says, what is the graph of f of x equals 1 over x? And of course, if you remember, the reciprocal function that we were dealing with earlier was just 1 over x. Now we're asking for f of x equals 1 over x squared. You could go ahead and plot points of this, but I want you to think about this from a logic standpoint. If we did this, if a normal reciprocal function looks something like this, but we were squaring the x now. So we have f of x equals x squared. So what happens here, 1 over x squared, whenever we square the x, if the x is negative, then we square that negative value, it actually ends up being positive. So our graph ends up actually looking like this. It flips the left-hand side, and so we can see that the domain and range are similar, and the equations, the vertical and horizontal asymptotes, are similar. We just get this flipped version of the negative values, and so you can see how does that change from f of x equals 1 over x. How is it the same? Well, it's different because the negative x values now have positive y values. And so that would just be a good generic way to state that. And so it's kind of an interesting little graph, and you could also do that on your calculator as well. So, all right, that's a good quick look at some different types of graphing with reciprocal functions.